Hello, my friends. To model a perch aquifer, and we are going to show you the technique because there is a certain technique if we want to model these type of aquifers. Okay, this is more related to some theoretical consideration because actually it has its numerical challenge. Okay, so we are going to use mf6Voronoi, and we have here the model limit. We have as well uh, a refinement area, okay, where we are going to do the refinement. Okay, great. And as well, we have an impermeable lens that is the one that is going to create the perch aquifer. Okay, so we have as well some regional flow. So this is the regional flow. And what else? We have a cross section. This is the cross section. Okay, and that's it. Okay, so let's start as in any other example. Let's start with anaconda prompt. Type anaconda prompt. CD documents. CD perch. No, dir. CD model perch aquifer, and then here Jupyter Lab. Great. Okay, so let's go here to scripts, and then we are going to create here on scripts a new that is going to be called part 0. Part 0. Okay, and here in part 0, what we are going to do something. Uh, well, we are going to initiate an output folder. We are going to import flow pies, and from mf6Voronoi utils, we are going to list templates and copy templates. Okay, first. Okay, so what we are going to do is that we are going to download, okay, from the repository. Okay, there is a tool where we can download the mf6 executable. Okay, so actually, uh, so let's see, for example, here we don't have the bin folder. Okay, we don't have the bin folder, and uh, what we are going to do is that we are going to initiate the bin folder, and as well, okay, first we initiate the bin folder. So actually that will create, if it doesn't exist, it will create a bin folder, and with this command actually will download the mf6 executable into the bin folder. So actually it's downloading that. So here you have the executable. So this is really handy. Okay, next we are going to copy the Voronoi perch, and as well we are going to copy the template perch. Okay, great. So here we have the Voronoi and the T. Okay, so let's go here to scripts and let's create the Voronoi. Okay, so how so we are going to call the mesh perch aquifer, and it will have a size of 20. in the reference area, it will have a size of 8, and the regional flow will have also a size of 8, and the limit is model limit. Okay, and there will be a multiplier here. Okay, great. There is some issues here with the, okay, so we generate, okay, there are some issues here. Okay, so we generate the Voronoi, and okay, there is some issues here with short size, so so we check, and there is a problem here. Okay, so we are going to fix these short sizes here by uncommenting and running this cell. So this is actually okay, so we have fixed that, and then we generate the output folder. Yeah, we generate the output folder, and we save the shape file there. Okay, and we can plot the shape file. Okay, this is the shape file where we have the regional flow and the refinement area. And from this shapefile, we are going to create the mesh. Okay, so we have generated the mesh. Okay, so far, this is not very different from other tutorials that we have done. Okay, so let's see here. Let's go to the model. To the model. Okay, so we run this. We run this. We run this. Okay, on the, oops, ouch. Okay. So this is located here. It's located here. Okay, this is on raster, model them. Okay, so the model will have 20 layers, and the layers will be located with this distribution. Okay, so where the layers, well, this is the distribution of the layers, and the bottom is 2300. So that will be here in model files, and this will be being. And just in case, here we are going to use continue underscore true, because we want that the model runs even that it doesn't find. Okay, let's see if it doesn't find. Okay, so what is the trick here? Okay, so we are going to model three steady state, three transient periods. Okay, the first one of 80 years, and the second and the third one of 30 years. Okay, and because, okay, if we model this on a steady state, okay, if we model this in pure steady state, we are going to find some problems, because actually the double water table is really hard to find, or is really hard to to obtain in a steady state. So you have to approach to a solution by running a really long a long transient stress period. Okay, so let's see, we run the GWF, great. We run this V, the EMS, great as well, this V, and then we can plot the top. Okay, and then here we can do the cross section, amazing. So we see the different layers, okay? In the initial, on the initial condition, everything is saturated, okay? So, mhm. And okay, so first here we have some key values for the first 6 layers. For the first layer is 4 10 to the minus 4. Okay, for the next 5 layers is 5 10 to the minus 6. For the next 11 layers or 10 layers is 3 to the minus 6. And for the rest is 7 10 to the minus 7. Okay, the first 15 layers are convertible while the rest is confined. Okay, but whatever that is inside the impermeable lens, okay, whatever that is inside the permeable lens will have, okay, for at this elevation, okay, will have, okay, this is the impermeable lens that creates the perch aquifer, will have a hydraulic conductivity of 10 to the minus 10, okay, and this is the K is K array, and the K33 is also K array. Okay, so and then we apply this impermeable layer in 2 layers because actually it's not that thin. Okay, and there is also an issue of interblock transmissivity that, well, if you want to represent better a perch aquifer, so actually, so it's better if you model that in 2 layers. That is my perception. Okay, so let's see, let's run this. Okay, so and then let's do a representation of your impermeable lens, the ones that create the perch aquifer, and that this is one. Okay, that is. So let's see here on the storage we have 3, where the first one is false. False. Okay, the first one is false, and the 0, 1, and 2 are okay, where everything is transient. Okay, we have recharge and evapotranspiration. Okay, and well, we are going to delete this. Okay, this one, and this one. Okay, so we define the intersection object again. Okay, we open the regional flow. Okay, then we apply the regional flow, and in this case it's really interesting because we on the regional flow, the head of the regional flow is actually on the attribute here, on the is on the attribute elevation. Okay, and these codes apply the attribute elevation. Okay, and for the elevation that is on the attribute elevation, it will get the layer and it will apply the elevation there. Okay, interesting. Okay, so we have here the layer and the elevation that comes from the attribute. So we can plot the elevation. This is the for one layer, for a given layer, these are the cells that are okay, and as well it will apply to the layer and the lower layers, okay, and the rest of the lower layers through the to the bottom of the model. That is great. So we run the output control, then we write the simulation and simulate the model. Okay, so that will take some time. So I will make a pause. No, it's running. So, okay, so it has finished. And then here we have we are going to use we want the latest stress period and the latest time step. Okay, so here we have the water table. Oh, okay. In this case, this is NSTP. Okay, that's amazing. And then we are going to plot the GHB. And as well, okay, so we can plot in this case, we are going to plot the water table. We are going to plot the water table. And this is, okay, see here we see the water table and as well the water table that is affected by the perch aquifer. Okay, so but on the cross section, we are going to plot the water table, but as well we are going to plot the heads in another layer, on the layer 15, for example. Plot array. Okay, GHB. Okay, and then this is something that I want to with okay. So what do we have here? Yeah. Okay, so the original water table is a surface that actually jumps here, okay? But the flow in this model is actually horizontal, mostly horizontal, okay? So, okay, so this is the water table that is actually affected by the perch aquifer, and we see as well a mounding here. But what also we also see is that we also see that there is another lower. Okay, so once we get deeper here, the head is actually at this level. So in act, okay, yes, so there is something that you have to take into consideration. Okay, when you talk about the Newton approach in Modflow6, okay, cells are never dry. Okay, those cells have a very low moisture. Okay, so a very low moisture. And in these cells, in all of these parts, the head is actually below. Okay, in these cells, okay, in the cells over here, okay, the head is above the cell bottom, so these cells are saturated. But for these cells, the cells are below the cell bottom. Okay, so these cells are unsaturated again. Okay, and then we find the second, what it will be the and affect the other water table. So that is how we can model the perch aquifer. Okay, so that was for, okay, and just we can plot the grid as well here, and this will be the tutorial for today. Very interesting approach of how we can plot the perch aquifer with Modflow6 and mf6Voronoi. Okay, and well, I hope that it will be interesting for you as well. Just a reminder to follow us. We have a lot of courses in our e-learning platform, that is e-learning Hatari Labs, hatarilabs.com. Okay, and as well we have, if you want to, okay, if you want to still contribute to our research, okay, you can be one of our Patreons. And that's it. Okay, please have a great day. All the files will be in the description of the video. Y que viva el software libre.